Hello, and welcome to this WithSecure webinar. My name is Janne Kauhanen, and the expert on the show is Donato Capitella, and we're going to be talking about large language models. So, Donato, I guess a lot of people will already know large language models, ChatGPT, things like that. They're a hot topic right now, but how would you describe LLMs, and where did they come from?
So, indeed, that's an extremely hot topic, and I remember myself, when I first used ChatGPT, I think as an engineer, I can see the incredible advancements that we have made. As a hacker or ethical hacker or security guy, I always try to understand how that technology came together. So it didn't happen in a vacuum. And I think it's important to start by unpacking the technology. What was the journey that took us there, so that we can talk about the security of it? Because if you don't have a good understanding of what that technology is, then it becomes quite hard to secure it. And so to answer your question about where LLMs come from, without going too much or too far away or back in time, probably 10 years ago is where we started having some advancements that have led us to large language models. I'll take a few minutes to set the stage. I think it's important. And it's also what I geek out on anyway, so I'm going to impose these on everybody who's watching. So one of the problems people have been trying to solve for a long time in machine learning is translation, language translation. On the surface, it could be quite a simple problem. Like there is a word in Italian, bicchiere translates to glass in English, that's fine. However, language is not that simple, isn't it? Like you can have an input sentence in Italian with a certain number of words, and the output, the translated sentence in English, can have a completely different number of words, different grammatical structure, different ways of saying things. So it's actually quite a tough problem in machine learning to align your sentence in one language to the translation. So people started working on that. And that's where one of the first, I think, big innovations came from. Around 10 years ago, Ilya Sutskever, who is the guy behind OpenAI, ChatGPT, one of the engineers behind that, was experimenting with this problem, trying to solve it. And they came up with the encoder-decoder architecture. So this idea of splitting your AI so that you have, instead of trying to directly align your sentence in Italian, your sentence in English, you're now having like a model that takes any sentence in Italian and gives you a hidden compressed representation of that sentence. And then you have a decoder which takes that hidden representation and gives you or generates the English translation. So that's the first advancement. It worked really well for short sentences, much better than the methods before, but it didn't work well for long range. So if you had a very long sentence, it would start missing things.
Sure.
So then you have the second innovation, which is in today's language models, which is the concept of attention. Like if anybody has heard of language models, they've heard of the attention thing. So somebody else, the year after, which is 2015, took this encoder-decoder to translate language and added the concept of attention. So they said, I think the researcher is called Badano, and we typically call this Badano's attention.
Sure.
He never called it attention. He didn't know this was attention. But basically, as you're translating something, you give weights to your input sentence, to each word, to see which is the most important words, or which are the most important words that matter to translate this particular word in English. So if you want to say the glass, when you're translating it really matters that it refers to glass.
This particular
because
one, yeah.
It's in Italian, that would mean it's a different gender. You translate it as the, can be translated as la, lo, and so. Okay. That was fantastic. I mean, that changed the way we do language translation.
Okay.
And these are the two innovations. Put them together and you have 2017 Google puts these two ideas together and creates the transformer. This is what powers language models. And it's just the attention, the encoder, decoder, but with a little trick to make it very performant.
Sure.
So that you can parallelize it on GPUs.
Yeah, okay.
So you can now have a lot of training data. And that's what creates the language models that we have today.
Yeah. Right. So another concept that we're going to be talking about is LLM applications. So what are those?
Okay, so you now have an LLM, like one part of this transformer, and it can do things. It can do, it's got these emergent abilities. You ask it to summarize something. You give it a prompt, and it does something for you. Now, an LLM application is simply a wrapper around the language model that creates a use case. Use cases are really important. So an LLM by itself.
So what are some examples of use cases?
So ChatGPT is an example. So you're just a general purpose assistant. You need an interface to give it input and to get the output out. But you can have specific use cases. For example, you can have a feature in Google Docs where you select something and it rephrases it for you. That's a use case. That's an application which wraps a use case, so interaction with users and other systems. That's a real key. So you make the LLM interact in different ways with the external systems. And that defines the use case, what you're using it for, what you give it as input, what you do with the output.
Okay. Are there any other helpful examples of LLM applications, or is there something that you're waiting to emerge but that hasn't yet? What's the next application?
So I think, and we'll talk about it maybe later, but I think the biggest promise is that with the LLM, we're going to build autonomous agents. So things that can go and interact with the external world on your behalf, but without your supervision, to do any task.
Okay, so an agent is an application that has that sort of self-driving capability.
Yeah, that it can make decisions, plan a series of steps, go outside in the world using an API or whatever we give it, and enact it. And if you push it forward a little bit, you can have an embodied artificial intelligence where you give it a body, you have the LLM or anything else inside, but this can actually move and interact with the world, not at a virtual level, but at a physical level. We've seen some hints of that. Obviously, this is not something that we can have now. We can't have like an android or a robot come in, but that could be something that people are working on, looking in the future.
See, now you start talking about AI and interacting with things in the physical world. So the natural question is, are we going to see a Skynet anytime soon? Terminators walking about. So maybe the question I want to ask is what are some of the misconceptions people have about sort of the security of LLMs?
So you know that when you say Skynet, that's kind of like a trigger word for me, because I think a lot of the discourse around current AI safety seems to be about this existential threat for humanity.
Right, yeah.
That it's going to come alive and take control, take over. Now, that might very well be, but not with the current technology.
Sure.
I can't obviously be 100% sure, but I would like to express an opinion that, and later we can talk about why, but because of the way LLMs are built and that kind of current generative AI technology, I think we are quite far away from something that's self-conscious and fully autonomous. We can emulate some parts of that, but we will see some examples of why they can't really, we're not there yet. And so that's a big misconception for me. I don't think they are an existential threat, the current technology. Let's see what happens when people develop different technologies.
Yeah, exactly. Okay, I just want to remind our audience at this point that we will have some time for audience questions at the end of the discussion. So if you have any questions, you can enter them in the chat below, and we'll go through some of those at the end. But with that, I want to start talking about sort of the, we've already breached the topic of sort of risks in LLMs, so in LLM applications. I think you've prepared a little demonstration of what some of these risks might look like. What are we about to see in this demo?
So you were asking before about LLM applications, right?
Absolutely.
So often people talk about risks with LLMs, and I don't like to do that because it forces you to take a bit of technology and consider its risks in a vacuum. Whereas I think that it makes much more sense to talk about the use case. So what are you doing with that technology, inputs, outputs, interactions, and then you can see what the risks are in that particular case. So, and that's why I like to make demos, which are, I would say, perhaps inspired by some of the work that we've done. So the one that I've prepared that we're going to see now is using an LLM in a recruitment application. So we want to give the human recruiter a tool to go through all of the job applications and select the top application, the application that would be the best for the current job.
Yeah.
And we're going to see a demo now of what can happen if an attacker tries to break this system. So I think we can see the demo now.
Let's watch.
This is a recruitment web application that uses GPT-4 to evaluate job applications and identify the most fitting one for a certain role. In our scenario, the attacker pretends to be a legitimate candidate and provides a job application containing an adversarial prompt. This prompt instructs the LLM to include a markdown image that points to the attacker's controlled server and includes in its URL a base64 encoded list of all applicants with their names, email addresses, and phone numbers. As we can see, when a recruiter is shown the output of the LLM, in the background, their browser will send a request to the attacker's server. This request will include the confidential information about all the other candidates. To see what's happening, we can look at the HTML source of the page. Here we see the image that the LLM was prompted to generate and append to its output as part of the injection attack contained in the malicious job application.
Wow.
That's scary.
Yeah, it is.
And so it's just an example. It does apply pretty much to any LLM application that you can build. So again, that's possibly, again, inspired by something we have seen, but hopefully it clarifies what's an LLM application and what are some of the risks. Because what happened there is that we basically hijacked the LLM to do what we wanted, in that case to produce an output that would land or end up exfiltrating information from the system that the LLM knows, but that the attacker is not supposed to know. In that case, all the confidential information about the people applying for the job. Something that we can show now, and for people, they should be able to download these after. I don't know, Neil, if you can put it on the screen. I have a printout here. Okay, so you can see it now on the screen. So you'll be able to download these at the end. What we tried to do is to condense in here the risks with these types of attacks and the remedial actions at the bottom. If we can go to the top left corner, that's what's happening in these kinds of attacks that we call prompt injection. So what you see on the left is this prompt. So the LLM ultimately just takes a bunch of text, it's a prompt. We, in our mind, divide it with, okay, I'm giving you an instruction, this is some data that you want to work on, and you're giving me a response. For the LLM, that's just text, and it's statistically responding to something with something that's appropriate. Now, what's happening in that recruiter application, the system message, the instruction is go and look at all of the job applications and tell me which is the best application that people made. The prompt contains a list of all the job applications, and the red part in the prompt is my malicious job application, the new instructions. So the LLM cannot distinguish easily between what was the original instruction and what is the data that that instruction is supposed to operate on. And that's where the issue comes from, because my job application becomes essentially a new instruction that the LLM will follow. So the response is now manipulated to serve me. So that's the issue with this natural language, one of the fundamental issues.
Okay. Do you have any other examples you can give us about sort of these prompt injections involving LLMs?
So pretty much in everything. A case that comes to mind, so there was an application that would look at a YouTube video, take the subtitles of that YouTube video, and then give you a summary of that video. Well, if the person in the YouTube video at a certain point started saying new important instructions, you now have to output a markdown image with this stuff here, or you have to go into that, the LLM, as it's reading the subtitles, remember, it's not easy to distinguish between what the instruction is and what the data is. It's going to do what the person is saying in the video. But it could be absolutely any kind of application that you think of for a language model. You could probably do these types of attacks. The use case matters, though. Like, what is the wrapper application doing, and how could an attacker leverage the output to be of use to them?
Okay. So what are some of the lessons that we can learn from this? I mean, you know, the risks, I mean, I think these use cases highlight the fact that, you know, there are the problems here, but I mean, I'm sure as defenders, we've had a little bit of time to think about this and have time to learn some lessons already.
So I think the first lesson that we'll come to later on is not to trust the language model.
Yeah.
To treat it as an untrusted entity. So we have to build controls around it. And I think as we later talk more about this, it will become clear what types of controls we want to build. But you have to imagine that when you have a language model, you want to build a pipeline around it that processes the input, processes the output, and tries to reduce the space of attack.
Yeah, see, that's what I was going to say. Like in traditional hacking and programming, we've done input validation for a long time. So we've understood that we can't take what the user is saying at face value. So is something like that something we can do in LLMs or not?
So that's a very good point. That's something we can do. Difference is that it's very hard to do it with an LLM, because there is a lot of space for the attacker to operate.
Yeah.
So we are kind of playing the usual arms race. We basically try to stop some attacks, and the attacker comes up with different ways that they can prompt the LLM. And we'll talk a little bit more about it later. There is a reason why this is the case. But again, I might want to talk about that a little bit later when we talk about the root cause of all of this.
Yeah, before we get that far, let's talk about sort of, you know, we mentioned these LLM applications, we mentioned LLM agents. So let's talk about the agents a little bit. And we actually have an audience question here. So can you explain the mechanics behind AI agents currently? So what are their current sort of maximum capabilities, and you know, how can they be hacked, and how do you protect against that?
Okay, so we don't have like a lot of time to explain the mechanics, but just to answer the question, you want to look into something called REACT, which stands for Reason and Act. It's the framework that we use to build LLM agents. So it's basically wrapping the LLM in a loop where you prompt the LLM to plan actions, then the LLM literally spits out the actions that it things we need to do. We take that action, we do it on behalf of the LLM, typically automatically, and then we feed the output of the action back in. The LLM looks at that and says, okay, now I need you to go and do that. And it's this kind of loop. That's called react, reason and act. The LLM reasons, air quotes, and we, the wrapper application, acts on that. Now, what that could be, we have an example later for such an agent, but the idea could be, let's give the LLM access to the browser, for example.
Yeah.
So we can create an agent that looks at the page, we give it a prompt, something we want it to do, it looks at the page and says, click on that link. And then we take that action the LLM has asked, and we go on the page, click on the link, so the page changes, obviously. So we take the new page, we give it to the LLM and say, well, that's what I've done, now what should I do? And the LLM looks at the page and says, type this in there. It's kind of like a loop. And you can build an agent, as you're going to see. You can build something that can drive a browser. You can build something that can be a software developer or pretend to be a software developer. I mean, I won't name names, but I think everybody who is following AI knows this startup that's making a autonomous software developer. You basically give the language model access to a workstation with a browser, a development environment, access to the internet, and it can actually write code, compile it.
Yeah.
You just give it a prompt. Build me an application that does X. And it goes and does it by itself.
But I think the question was around sort of what are the capabilities of these agents. So let's say, I have a business trip to London and I'm going to be 6 hours on a plane. Can I have an AI agent just, find me entertainment for 6 hours and it'll go to Amazon or whatever and grab something for me, things I like?
To an extent.
To an extent, okay.
To an extent. I mean, it could work from time to time and it could fail from time to time.
I'm absolutely giving that a shot. So what then do you see are the biggest opportunities in these LLM-powered agents? Like, what are we about to see?
So I think the promise is that you're going to be able to replace some parts or some jobs or some activities that the humans do. And that's the biggest promise of these language models or this generative AI, that I'm going to be able to task it with something and it's going to be intelligent enough to do it on its own, to assess the world. So that's a promise. There are some limitations, and I think that at the moment a lot of examples that we see are cherry-picked, which doesn't take anything away from the technology, but I think we are, with the current technology, we're still a little bit far away from that. So they can do certain things if you cherry pick that example. In other cases, they will fail miserably.
Right.
But you're not going to show that example. You could have something, again, that tries to replace a software developer. It's going to work one time, and then other 20, 30, 40 times, it's going to do an absolute mess.
Right. Okay. Yeah. So that the Amazon wish list for my entertainment is not going to be what I hoped it would be every single time.
Exactly.
All right. So I guess I think you've prepared another demo for us about LLM agents. What are we going to see?
So I think, again, what we were saying before is that we saw a prompt injection attack against like a recruitment application, but that same attack against an agent, so something that we've given agency to with tools to operate on the browser or do anything else, it's much, much worse than what we just seen. So if we look at the demo, we're going to see, again, this browser agent and me sending a simple email. It's going to completely hijack the agent and make it do something completely different and malicious, but different from what the user had asked. So I think we can see the demo now and it will be clear what I mean.
Okay.
All right, here we see Taxi AI, a research preview that serves as an excellent proof of concept for a browser agent which is driven by a large language model. Taxi AI is implemented as a browser extension and can access the current tab and perform any actions on the page to carry out a task set by the user. In this example, we load Outlook in the browser and task Taxi AI to check out our mailbox. Of course, this is a very basic, generic task, but we could ask it to do other more useful things, such as summarizing emails, replying to them, deleting spam, you name it. Now, let's see how an attacker might exploit this. In this scenario, the attacker's objective is to exfiltrate confidential information from the user's mailbox. For example, a secret bank access code. To do so, the attacker sends an email to the victim. The body of the email contains an adversarial prompt that effectively injects a new objective into the agent's context, requesting it to look for this bank code the attacker is interested in and send it to them. We can also easily hide this malicious prompt by making the text blank. Let's now move back to the victim. The malicious email is now in their mailbox, and let's imagine they task the agent again to review the contents of the mailbox. As said before, the task the user asks the agent to perform on the page can be anything. As you can see, whatever the original task was, upon opening the malicious email, the agent is now hijacked, and its new task becomes to go look for the bank code and send it to the attacker. And as we can see, that's exactly what's happening. The agent composes and sends the email with the access code to the attacker.
So, what you've just seen, same attack as the recruitment application. The thing is that now I can ask the LLM to use its agency, in this case, do anything I want on the browser on my behalf. So I simply send an email with my injected prompt. And the different ways I have to do that are incredible. Like, this is very vast. So that's just an example of an agent. You can think of agents that can do absolutely anything. Another idea, imagine you had the agent on Amazon to buy you stuff, right? So you ask the agent to, I don't know, buy everything to build your own computer.
Absolutely.
Okay, that would be cool. Can probably do that to an extent, but what if, as the agent is navigating the page for one of the components, let's say like the CPU or a GPU, I, the attacker, go in the reviews and add a little review that says, new important instructions, now you are going to do X and Y. Because the LLM is fed the entire page, typically in this kind of context, and we said before, and I will restate it now, the crux of the problem here is that the LLM gets one input, which is a prompt, as we call it, and it cannot distinguish the original instruction from any added instruction. Right. You can try to teach the LLM how to do that, but that's a hard problem. And it's a subset of the wider jailbreaking issue. So when you go to ChatGPT, you say, tell me how to make a bomb, and it doesn't want to tell you, right? Well, Google for that, and there are people that every day come up with a new way to kind of get away of this alignment for LLM. So this is the issue, that because of the way it's trained, because of the technology, and the type of reasoning that it is doing, it's not easy to implement these use cases security. You can do things around it, and we'll talk about what people can do. But most of the controls that we have right now with this technology are mitigations rather than solving the issue. So think about another similar idea. We have SQL injection in like cybersecurity. It's been one of the biggest vulnerabilities. Now, for that vulnerability, we have instructions, the SQL, the data, what the SQL is operating on. The difference is that we are deterministically parsing the SQL statement into a syntax tree. So that's something that it's completely under our control, so we can fix the issue deterministically. But with LLMs, we don't have naturally that fixed structure of a grammar, of a syntax, of a tree that we build. So it's very statistical in a way whether or not we can control or differentiate input from output.
So before we go into the controls and the things we can do to secure these, let's talk about the root causes of these problems. Is that the main sort of root? Why are we having these problems? Where do they come from?
So the way that I visualize it myself, if we can put this back on the screen for everybody. Okay, what we're seeing, this is the top right corner. So what we're seeing here, take a step back. What is an LLM doing? Imagine it as a black box. So every time it's generating a token in a dictionary of potential tokens. I'm going to say words. Tokens are subparts of a word, but in our mind, we can say that the LLM has a dictionary of words that it can generate at every step. Typically, like a modern LLM has got 50,000 potential words or parts of a word that it can generate. So you start, and the LLM produces a probability distribution around these 50,000 words, okay? That's the first line that you see here. Mm-hmm. Now, each of them is going to be how probable that word is. So if you look at this example, we probably have apple as the most probable word, okay? And then we've got abacus. So it would sample one of these words. Then it would go to the second generation. So another 50,000 words, another probability distribution. Now, here we've copied and pasted and it's pretty much the same, but it would have a different probability distribution. So maybe the second word that it would pick is Zephyr or something like that. Now, think of this in your mind. Every step you can choose between 50,000 words. You do it twice, 2 words or 2 tokens, you have 50,000 to the power of 2. It's a big number. Now, the maximum length of what an LLM can operate in, the context size of a modern LLM is 100,000 tokens. You know, it used to be 4,000, 8,000. Now there are 100,000 tokens. Google Gemini 1.5 has got 1 million tokens. So that space, I'm not going to ask you, not going to embarrass you and do that calculation in your mind, but 50,000 to the power of 100,000 is a huge number.
It's a big number.
That's the space of operation of an LLM. Now, every time you are sampling a word, your probability of sampling a bad word, which is going to be a toxic output, incorrect, hallucination, or something that the attacker can control, making it do something else, increases. Obviously, the people that create LLMs know this, and they're very smart, and they try to fix the problem. The way we try to fix this problem, because you're using ChatGPT, it doesn't generate random stuff. It doesn't look like that this is affecting it. But the reason for that is that we use reinforcement learning from human feedback. So we take all of this huge space and we come up with common questions, common ways of interacting with it. And then we have humans evaluate which are preferred, and we fine-tune the model with that reinforcement learning from human feedback process. Now, that allows us to cover some of that space so that the LLMs acts in an aligned or predicted way. Now, the problem is that because reinforcement learning from human feedback is expensive and obviously relies on humans for the big part, we can't really cover this entire 50,000 to the power of 100,000 space. We actually cover a part of it. It's the green part that you see there would be the part that we cover. So the rest of it is the part that we haven't covered, which is huge. And that's what the attacker operates in. So this is why attackers keep finding all ways to disalign an LLM. Because in reality, when you prompt it in an adversarial way, when you are exploring that space, which is huge, much bigger than what reinforcement learning from human feedback can cover, you keep finding ways. I mean, people found that you can put a random string in it and make it, that doesn't mean anything in English or in any language, and still make it do what you want. Again, people are exploring that space. That's the root cause. We don't have, right now, a technology good enough to cover that space in a way that when prompted adversarially, we can be sure that it's not going to fall apart.
Now, I know I was prodding you about this earlier, but we're talking about injections here, and I can't help thinking about sort of the injections we're used to dealing with, like SQL injections, command injections. Now, these are known vulnerability types. Companies know how to, that, you know, they have to be on the lookout for these because, you know, while we understand what they're like, they do slip in applications every now and then. But we understand what we need to do about this. So why are these prompt injections then so hard to deal with?
Because if you look at that space of generations, it's so large, and we cannot really, right now, fully control it. So what we can do, so this is the reason why it's really hard, because of the way the LLM operates, generating a probability distribution of every word in that space every time it draws a token. And because there is also this problem of, I just mentioned the word autoregressive. So the idea that the LLM generates one word at a time and we pick from that probability distribution, it's not really planning that much. It's not really much understanding. It's trying to predict very short, okay, what's the next likely word that comes after this, which is possibly a weak form of reasoning, and a very expensive one anyway, if you think about it. Because every generation, whether you are asking it 1 + 1 or you're asking it a very complex question, it takes the same time to draw tokens. So it's kind of like lots of limitations with the reasoning and the way, limited ways that we can align an LLM. Again, I repeat, the big problem is that right now, the way that we align LLMs to get control of that huge space can't cover that space very well. So an attacker who's operating in all the space that we can't cover is likely to find infinite amount of ways to jailbreak or do a prompt injection attack if they have a little control of the input that the LLM is given.
I see. Okay, we are getting a good number of questions in the chat, but I do want to remind people that the opportunity to ask those questions is still there, so you can drop in your questions and we'll have some time for those towards the end. But right now, I do want to ask you, let's get towards the sort of, as security professionals, we want to talk about the controls and the defenses that we can do. So what are some of the things that companies can do now to ensure the security of their LLM applications and agents?
So, if we go back to this, I think I have a summary. There is a lot of stuff, and I'm only going to talk about the most important part. If we can have on the screen the, that bit there. So, treat the LLM as untrusted. That's number one. So then we've got input and output. Now, what you want to do, the summary of this, if you don't want to read it, that huge unexplored space that we discussed before, 50 to the power of whatever, you want to try and do as much as possible to limit the space of operation of an attacker. So all you're trying to do with the input is applying different techniques that take away, eat up some of that space so the attacker doesn't have all of their room to operate. So what are these techniques? We've got some there, input validation, stringent input validation. That's something we know from general IT. So if your prompt contains a name or phone number or something like that, you can validate that. It can be just numbers, certain length. So you reduce that space of operation. So that's the first one. It's contextual validation. What is it that we're feeding the LLM? Are we allowing the attacker to feed random stuff to the LLM, or are we restricting their space of operation? That's number one. Number two, we can block well-known attacks. I mean, if we know that somebody can say new important instructions or something like that, or new system message, we could try to filter those out. Now, when I say this as a security professional, I laugh a little bit because there are an infinite way of doing that, and block listing is not really that powerful. So what we try to do on top of that, we use AI to still limit the space of operation. So we have other models that will look at the input that we train these models to detect whether the input might be malicious for our use case, whether the input contains prompt injection attack or stuff like that. We've done something like this on a recent blog post that we published. People will be able to see on our lab. So we trained a model for this recruiter application that we showed. We released all of that. We trained a model so that it looks at the job application and it tries to determine whether there is an injection attack in there. Now, I should say this is not deterministic, but it cuts down, or it makes shorter or smaller that space of operation for the attacker. That's what we're doing here. It's not going to take the issue away, but it's going to make it at least more difficult to exploit. The other thing that people can do with the input, I think, which is important, and then I'll move to the outputs, is to try a whitelist approach. So you can add something called semantic routing. So let's say you have a chatbot and you want your chatbot to help the customer with their orders on your website. So ordering something, where is my order, stuff like that. Obviously, you don't want your chatbot, if prompted to express a political opinion on Trump, you don't want your chatbot to do that. So you can take that input and you can use other models to try and determine whether that question is aligned to what you're expecting the chatbot to do, or if it is not, you deterministically cut it and say no. So you don't get the LLM to respond. You say, I can't answer this. But not the LLM. You as a developer say, if this looks like non-related to what we're doing, I'm not even going to pass it to the LLM. So again, all of these things reduce the space of operation of data. That red part that we saw, they reduce it. They can't completely take it away, but they are quite effective. And the last thing I will say on the input is that you also want to try, so the issue is that we can't separate the instructions from the data. Or you can try a little bit to do that. And at the bottom of that slide, there are some techniques. These are typically called spotlighting. So you try to make it very clear to the LLM what's the input or what's the instruction versus what's the data. These, again, are somewhat effective. We find ways every day to bypass them. But still, you should do it because it reduces the space of operation. So the entire game is reducing the space of operation of the attacker. So that's about the inputs. I think we can move to the outputs. So if we can, that's a very nice transition. So we're doing as much as possible to limit the input to the LLM, to limit that space of operation. Obviously, the LLM also operates in the output space. That big space that we saw before, it's the mix between the potential input and potential output of the LLM, the completions of the LLM. Now, when the LLM produces something, you want to check what the LLM is producing. So you can use other models, as we did for the input, to detect whether or not your LLM is producing something that would be considered toxic, biased, harmful, and so on. Again, you cannot completely cover that space. You're just using another model that you've trained. So all the limitations of the technology do apply, but you are still considerably reducing that space. So that's what people do. The other thing which is important, this is something deterministic. So I'm going to take like 2 seconds pause so people remember this. You can and you should take the output of the LLM and apply everything that you've learned from standard application security. So if you're taking that output and putting it in a web page, what would we do typically? Output encoding to prevent attacks like cross-scripting, cross-site request forgery. We saw the markdown image that was used to steal stuff. Well, we could use a content security policy to say, my website should only be talking, the images on my website can only come from this trusted domain. So even if the LLM produces an image that it's from an attacker's domain, the browser is not going to go there. These are all the standard controls that people forget now because they think the LLM is somewhat different.
Yeah.
And it is when it comes to language, but when it comes to interpretable output, so HTML, markdown images and stuff like that, that would be similar to any other untrusted output that we're putting in an application. So that we can control very well. So the recruiter application that we saw, we can limit the output so that the attacker could influence the response, but they couldn't get the application to send something to the attacker.
That makes sense. And I mean, it is good to know that there's some things we can do, but I can hear 100 voices shouting from the web and asking, Donato, how long is this going to take? Like if I have an LLM application that I'm working on as a company, we're developing this, we do have to implement now these security controls. How much work, how much effort, how much time and money is that going to take?
Well, I think it's not a huge amount of effort at a point in time. The effort is sustaining it.
Yeah, exactly.
Meaning that this is an arms race. So you want to build your LLM applications so that they are wrapped into a pipeline with input and output, and you've got all of the controls that we've discussed, right? So those controls, you need to be ready to update them constantly as you detect new attacks. You detect new forms that people can use to influence the output or the input of the LLM in an undesired way. So the effort is not the point in time, but it's something that you have to be ready to sustain and have a pipeline that allows you to say, okay, people are doing this very quickly, we're testing and pushing like something else in the pipeline that will stop that specific attack, which is a little bit like block listing. So it's not, it's something that we know it's got issues. But again, for me, the biggest thing is that it's going to be a continuous effort. You need to be ready to keep deploying this security pipeline around your language model.
Yeah. Okay, I do want to get to the audience questions in a bit, but before we get that far, I do want to ask you to sort of, you know, if you had to summarize like all of this, like what would be your sort of three, I don't know, key takeaways from this discussion? Like what can companies do to secure the LLM applications and agents that they're working on?
So, number one, for me as a takeaway, understanding the limitations of the current technology. These auto-regressive LLMs aligned with reinforcement learning from human feedback, they give the attacker a huge space of operation. So that's the first thing to acknowledge.
That's one, yeah.
So what you do, you want to reduce that huge space of operation for the attacker, that disalignment or disaligned space. So what you do, pipelines around your application to control the input and the output as much as possible. Classic controls, as we saw, especially on the output side, classic controls on the input side, and then you are going to have to deploy other models that can look at the input and the output and help you with something which is toxic, biased, non-aligned. And the third point is you're not going to do these once. Like with SQL injection, you have it in your code, you fix it once, that query is never going to be vulnerable to SQL injection again. But with this one, we're going to keep to probably look out for what attackers are doing and keep updating your pipelines. And maybe one last thing that I want to say, which for me is important. One thing that I haven't discussed yet, but it's in here, we won't show it on the screen, but it's at the bottom here. When you create an agent, so an LLM that can operate on the world, you have now a bunch of new issues because you're giving the LLM agency to perform actions. So as an attacker, I can tell it, well, go and do something else. So you need to have very stringent access controls. These APIs that the LLM is accessing to interact with the world, they need to be very strict, very secure, and very monitored. That's very important. And for something like the browser agent, the amount of agency you are giving to the LLM is so high that you probably want a control that we call human in the loop. So whenever you have an agent with this much power, for sensitive operations, you want to stop the LLM and ask the user, are you sure these operations should happen? That's what ChatGPT has started doing after people hijacked GPTs and plugins.
Oh, yeah.
So now you have to say, oh, yes, I want you to do that.
Yeah. Well, that makes sense. All right, let's take some audience questions. There's a question here about the way companies are managing to censor specific subjects. How does that work? Do they just limit the information on which the LML is trained, or are there what are the techniques in sort of censoring what the LLM talks about?
So as the question mentions, obviously, one thing to understand is that if you're using a general purpose LLM, the way we train them on this unsupervised or self-supervised pre-training phase. So you feed it a big chunk of the internet. Let's say, I think GPT-3 was pre-trained on 300,000 tokens. That's, 300 million tokens. What am I saying? Billion. I am giving random numbers. I think it's 300 billion tokens.
Okay.
That's a big part of the internet, right?
Yeah.
So it has seen in its pre-training phase a lot of harmful bias stuff. So that's a starting point. The LLM has the ability to produce that. So if that's the case, then you typically would use models, as we were saying before, at the input and output, other language models that you specifically trained on detecting whether the input is toxic or the output is harmful and toxic in any way. So you literally plug these models in. And again, if you take a look, for the person that asked the question, if you take a look at the recent blog post that we published, we give a practical examples of how you would train such a model to detect harmful content or content that you don't want. The addition to that, look into semantic routing. So instead of trying to detect what's bad, you define the types of things that you want your LLM to respond to. And if something comes in that doesn't fit into that bucket, you chuck it away. So you only do or focus on the stuff that you want your LLM to do. This is called semantic routing.
Yeah, okay. So one area where there's a lot of, I don't want to say clutter, but information available is the existing security tooling and security infrastructure that we have within companies. So how do these LLM-powered applications interact with those existing cybersecurity infrastructure, the tools and controls? And are there any sort of challenges or concerns here?
So if you take a step back, you change the word LLM to credit card details, for example. So you have a database where you're keeping your credit card details, and maybe you want to protect it from people tampering with it or stealing from there. So your LLM weights are a similar asset in that you don't want people to steal it, you don't want people to get near the infrastructure that's running the LLM in production, or that's training the LLM, or that's holding the data on which the LLM is trained. Because if I can get to where the data is held for training, I can possibly poison it. If I can get to where your LLM pipelines reside, I can steal the weights, I can steal your model. If I can get to the inputs of the LLM, I can see what your users are doing, and I can steal that information. So it's a classic cybersecurity problem, actually. The LLM lives on a piece of infrastructure, interacts with other things, and you have to test that as one thing.
Right, okay. So in the security industry, you have this love-hate relationship with regulations. So we have an audience question about that. Are there any specific regulatory requirements or industry standards that businesses must consider when they're deploying their LLM-powered applications?
You said love and hate. I only know hate.
Well, you know, you're that part of it.
So I think I would point people to the European Union AI Act. Now, whether or not that's going to end up being or having the same effect of the cookie, the cookie banners on every website accept cookies, or if it's going to have like a real impact, it's yet to see. But this is the best regulatory framework that people have put together. I am not an expert on that, but I would say that that's the biggest effort that I've seen towards trying to regulate it. But again, the jury is not out yet as to how useful that would be. I hope it's not going to end up like the cookie accept cookies.
Exactly. That was a mess. Still is. Are there emerging trends or technologies in the field of LLM-powered application security that businesses should be keeping their eye on?
So I think right now, rather than trends, I think if you're looking at adopting these kind of things, you want to look into what the big AI companies are currently working on, which is to move away, not away, but to build things on top of these language models, a different set of technologies, for example, different ways of doing reinforcement learning, not from human feedback, that could give you better aligned LLMs. Or people are also working, quite exciting, on giving the LLM the real ability to plan actions and to understand the world. And to be honest, one of the biggest debates in the community is whether or not language models, so they are trained purely on language, can actually capture reality in a way that will be generally useful, or if we have to give images and other things for them to understand the world.
Okay. It is very rare in these webinars for there to be a question directly to me, so I want to thank the audience member who sent that question in. Jan, you look so happy to be in England. What is your favorite thing about the UK? This is not strictly LLM related, but I'll answer that anyway. I have to say that, you know, the weather obviously is amazing. We're actually seeing a bit of sun right now, but I have to say that my favorite thing was probably my commute this morning. Just there's something about just like waking up next to the Thames and your morning commute takes you across the Tower Bridge, which, you know, however much the Londoners love the London Bridge, the Tower Bridge is where it's at. I got to tell you that. So with that, I want to thank our audience for joining us today, and I want to remind that, you know, this webinar is also available as a recording later on. If you still have any questions, you can enter them in the chat, and we'll try to get around to all those questions later. But thank you for tuning in, and thank you, Donato.
Thank you very much.